Jai Hind all, this is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is lecture series on analog signal processing, and today's topic is sensitivity. In analog signal processing, we have discussed the various components of analog signal processing, and then we have discussed the design of analog signal processors also, some filters. Now, most of the time when we design a filter, we need a RLC, and we have changed the value of L with some other type of circuits that we will see later, like GIC and gyrators. So we are taking R components, C components, and the amplifiers values, generally op-amp or transconductance. So we take its appropriate value. For example, whenever we take resistance, the resistance is always specified by plus minus some tolerance. So its value can vary with that plus minus X percentage. So we cannot avoid the exact variation of these components. We cannot see how much these variations can be there in R component or C component. So we have to tune to the nearest possible value. So whenever we tune, we need tuned circuits. These tuned circuits we will see later on in the course. These tuned circuits are again some op-amps and transconductance amplifier circuits, and they can give appropriate values, but they are costly. So but at the end, we need to have a circuit which can work as our requirement. That means the omega naught and Q should be exactly as we want, or that can be tolerated to some value. Now, the shift in the values of R and C, we have seen that the inherent value of operational amplifiers, the gain values of operational value or operational amplifier also changes the pole positions. Also, they give the parasitic poles. So this gives shift in pole location, phase, or the magnitude response of the circuit. As a result, the circuit can be different from our desired circuit. So from this deviation of the RC components, the different performance parameters may vary. So we should answer that how do the component tolerance affect the circuit response. So if the component tolerance is varying our response greatly, we have to adjust using the circuits. If the tolerance of the components, like if R is varying 1 plus or minus 1% and we can tolerate it, then we can neglect it. Then we need to have how do such changes relate to the filter specifications, that is omega naught, Q and gain. So if we have a R component or C component which is not related to omega naught, Q or gain, then we can neglect that component. Or if they are varying or they are changing any value of these specifications, we have to take its value in consideration. Then we have to find that how do the response of different circuits in the component tolerance, how reflect the component tolerance. For example, if R is varying, then how the other components are behaving. So if they are, if one circuit's component is changing with the other components, the overall transfer function, overall response of the different circuits is varying, then we have to consider this component tolerance. Lastly, we have to find out that how do such changes related to the preference of one circuit over the other circuits. For example, if there is a cascading, the first cascaded circuit will have the large extent effect than the last stage components. So the first stage components in a cascade will give more changes related to the last stage of cascaded amplifier. So we have to consider the first stage more seriously than the last stage of the cascaded design. So what we need to predict these measures of sensitivity so that we can have predict these components, measure of these components, which is sensitivity. So we have to predict the sensitivity to answer these all questions, to answer these all things. So what is sensitivity? Let's suppose we have a circuit given by this equation. This circuit can be any filter or any circuit which is required for analog signal processing. Let's suppose this is the low pass, high pass or band pass filter. So if it is a filter, this will have R, C and L component which can be replaced by the other active components. So if this is a circuit which is consist of R and C components, let's suppose the R component is varying. Let's suppose the R component has a tolerance of plus minus some X value. So R's value is varying for that extent. So we can take this circuit as the circuit plus the R component which can be taken out from that for the study. So we can represent this circuit as circuit of RLC circuit, or this circuit with C and R component, C and other active component in place of L, and R can be taken out for study, and this value of R may vary. This is expected to vary due to its inherent property. So we can write there that the transfer function of this circuit, let's suppose the transfer function is equal to V2 by V1. Now this transfer function is a function of R also. So if I want to write Ts is equal to V2 by V1, the transfer function is also function of this R. So I have to write V2 by V1 transfer function is equal to St comma R, as the transfer function is also a function of R. With the change of the R, the transfer function will also vary. Similarly, the omega naught will also change with the change in R. So I can write omega is equal to omega naught into R. This R is varying, and the variation in R will result in change in omega naught. Similarly, we can say that Q is function of R. Now this R is a small variation. So let's take one parameter out of this one. Let's suppose we are taking this transfer function. So I can write the transfer function TRS, as R is very small, so variation in R can be given by Taylor series expansion. So I can write in the Taylor series expansion as Ts comma R naught plus the differential of Ts R by del R. where R naught is the initial value of R. So this differentiation is at the R naught into dr. So here this Ts R naught is small change in T when R is R naught. So it can be given as del Ts R by del R when R is equal to R naught into dr. So I can write the transfer function in this way by using Taylor series expansion and dependency, considering dependency on R. Similarly, we can have the change in omega naught and q naught, and we can have expansions for Taylor expansion for omega naught and R naught, q naught. So we can rewrite this equation as del T by T into R by T into del T by R into dr by R. If we consider this equation, let's suppose this is del T, this is equal to T by R into dr. So I can write it as del T by T into R by dr by R. So I can write del T by T is into del T by T into dr by R and R by del R. So if we see here, this is changing the resistance with respect to the value of the resistance, and these are the small changes in the resistance. Here this term, if we take out, let's suppose this is STR. What is the meaning and what is its value? I'm just explaining. So we can say that where STR, S subscript T and this script R is equal to R, this value R into del T upon T into del R. Or further we can change it like in this way for our simplification, for calculating or for reducing some results from this equation as del Ts by del by T upon del R by R. So this equation, this parameter is known as sensitivity of transfer function with respect to R. So this sensitivity is sensitivity of transfer function T with respect to R, and is given by the change in T with the original with the actual value of T, desired value of T, and ratio of R, change in R with the change in with the actual value of R. So we can say that the sensitivity of T with respect to R, it is the ratio of relative errors in the function of the Ts, relative error of function Ts to the relative error of the resistance or any other component. Any other component means if we have C component that which giving some sensitivity due to the variation in its component. So I will write STC is equal to del T by T upon del C by C. Here we are considering that only R is varying, so I have del R by R. So for small but finite difference, if we have a small, this R is small but it is a finite, so we can change it to we can change R to del R and R to T to del T. So this equation can be written as del T by T is equal to STR into R by R, del R by R. So this gives that the relative change in R results in relative change in T. So which is change in any change in R will give change in T, but this change is the change in components value into STR. So this means the change in R value will give change in T value with which is STR times the original value. The relative change TL, for example, TS by S is also called the variability. That means del T by T is the variability of transfer function T, and del R by R is the variability of R. So from here we can say that variability of transfer function T is equal to the sensitivity multiplied by the variability of component value. For example, here component value is R. So this is the relationship between sensitivity and the variability. Now we have discussed initially that the sensitivity of the different components will have different values. Now we have different positions, different configurations through which we can join the different systems. Let's suppose we have open loop of the systems. For example, here we have two systems, T1 and T2. The overall transfer function of this open loop circuit will be given by T is equal to T1 into T2, because they are in cascaded form, so the transfer function will be multiplied. That means total transfer function T is equal to T1 multiplied by T2 value. And T2, let's suppose, is varying. So it is clear that T2 is affecting the overall transfer function. Now let's suppose, let's see the sensitivity of T2, sensitivity of total transfer function over T2, sensitivity of total transfer function T with T2. As T2 is varying, so the transfer function is also a function of T2. So we can say that we can calculate the transfer function with respect to T2. We can find out the sensitivity of T with respect to T2. So what is its transfer function? Its transfer function is variability of one component with the variability of the other component. So I can write it as del T by T divided by del T2 by T2. As from the previous case, we have seen that this will be equal to the del T by T divided by del T2 by T2. The variability of total transfer function with the variability of the component or the value which is varying. Here T2 is varying, so I can this equation can be rewritten in this way. Now if we see here del 2 by del T by T, it can be given by T1. Del T by T, it is equal to T1. So I can put the value of here as T1. So in place of this value, I have written T1, and the value of T can be written from here as T1 multiplied by T2. So T1 multiplied by T2. Both will be cancelled out and it will give 1. So both will be cancelled out and it will give equal to 1. So what is the result from this? What we can reduce from this result? The first thing is that the change in T gives the sensitivity of total transfer function with respect to T2 is equal to 1. Or from here we can say that the change in T1, total T with respect to T2 is 1%. Or we can say in another words that 1% change in T2 will result in 1% change in T, total transfer function. So one change will result in the other change with the 1%. Now another configuration is the closed loop. Let's suppose we have this closed loop transfer function, and again let's suppose the closed loop has gain h. Let the transfer function total transfer function, the varying component is T2. This T2 is varying. So if we say the closed loop transfer function, if the output is V2, input is V1, the loop gain is H, closed loop gain is H, the system is open loop system is transfer functions of T1 and T2, where T2 is varying, then the total transfer function, can be given by T by 1 plus HT1 into T2. Now we want again the total sensitivity of the total transfer function with respect to the varying component, which is T2. So the sensitivity of T with respect to T2 again can be given by del T by T divided by del T2 by T2. If we put the value of del T over here from this equation, it will giving as T1 into 1 plus H1 into H2 minus T1 T2 HT1 divided by 1 plus HT1 T2 whole square. Or this will cancel out and it will give 1 upon 1 plus HT1 T2. So the sensitivity here is not equal to 1, but it is 1 upon 1 plus HT1 T2. Now if we see here, we have, let's suppose if we have transfer function such that the gain is high, the loop gain is high, then we can have this value which is much larger than 1. The loop gain, the transfer functions T1 and T2, the multiplication of all these values will be much more larger than 1. So we can neglect this component, or we can say that it is equal to 1 upon 1 plus H, 1 upon H. So the sensitivity will become ST with T2 as 1 upon HT1 T2, the total HT1 T2, because this one is much more, this value will be much more smaller than val 1, because this value HT1 is much more greater than 1. So the overall sensitivity will much more less than 1. Or we can say that the closed loop sensitivity is decreasing with respect to the open loop. When we consider open loop transfer function, it is always giving 1%, but when we are using a closed loop sensitivity, the transfer function sensitivity will be always much lesser than 1. So let's take an example how the sensitivity is varying for the open loop and the closed loop by using this circuit. I'm taking this example from the textbook that we are referring. So this example gives that we have an inverting amplifier which has R1, R2 and V1, V2 are the input and the output voltage. We have to find out the sensitivity with respect to R and the other components. Obviously here we have R only, so we have to take the sensitivity with respect to R. So first of all, let's take what is the transfer function, so that we can find out the transfer function dependency with R1. So first thing is to find out the transfer function. Transfer function is output voltage by the input voltage. For this inverting amplifier, we have the transfer function, which will be R2 by R1 divided by 1 plus A into 1 plus R2 by R1, which is a standard form of inverting amplifier. If you take low frequencies, let's suppose it is low frequency gain, then we can replace R2 by R1 by G0. So amplifier's low frequency gain is G0. We can say it is G0 by 1 plus G0 into divided by A. A is the gain of this amplifier. Now, this transfer function can vary with the variation in resistance R1 as well as with the variation in resistance R2. So we have to find out the sensitivity of transfer function with respect to R1 as well as the sensitivity of transfer function with R2. So if we find out the sensitivity of transfer function T with respect to R1, it will be del T by T upon del R1 by R1, or I can say R1 by T into del T by del R1. If we put the value of this transfer function T over here, so I can put its value from here to this value, and we have to take derivative with respect to R1, so it gives this equation. The derivative of this with respect to del R1. So this gives R1 by T, this is inverting case, so it will be minus into minus of R2 into 1 upon 1 plus A into divided by R1 plus R2 divided by A whole square. Now if we have to take some again some assumptions, let's suppose we have A as infinite. As A's value is always much higher value, so we can take A as infinite value. Now when A is infinite, so this whole value will go is equal to 0, and this will give R1 by R1, which will be cancelled out, and it will be equal to the sensitivity of R with respect to R1 will be equal to -1. So this value will R1 will be cancelled out, and this value will be equal to 0 plus 1. So this will be R1 into 1. This one value will be 0. So R into 1, R multiplied by 1 will be R1. Here it will be R1 plus 0. So R1 will be cancelled out, will be giving -1. This means again the value that the change in 1% of the change, 1% change in R1 will result in 1% change in transfer function. Now minus sign shows that with the increase in the value of T1 R1, there will be change in the transfer function value by opposite direction or in the negative direction. Similarly, we have the other component, other value that we are going to find is sensitivity of T with respect to R2. So again, taking del T by T divided by del R2 by R. Here R2 is required because we are finding sensitivity with respect to R2. Putting the value of T over here from this equation and taking derivative, then taking assumption that alpha is infinite. There are calculations, I'm not going with that, but we can calculate it to find out the result as 1. So now the result is 1. Now we can deduce what is the meaning of 1. This is equal to 1. So if we conclude this example, we can say that the change, 1% change in R1 or R2 will cause the total transfer by one value. If R1 is changing, it will be -1. If R2 is changing, it is +1. Since we need accurate resistances, the value of sensitivity is acceptable. To evaluate the sensitivity of op-amp, which is also a component which can also vary, we have assumed that A. So we can have the sensitivity of transfer function with respect to A2, right? Because A is also a component that can also vary. So we have to take the sensitivity of transfer function with op-amp also. So if we see in this figure, we have 3 components which can vary. One can R vary, other can vary R2, third thing can vary is the op-amp or op-amp's gain. So we have find out R1, R2. Now we can have to find out the sensitivity with respect to gain 2. So sensitivity of T with respect to A will be again del T by T into del A by A, and put the value of T. Here I am putting in terms of gain, so that we can calculate it in terms of gain only. So and taking its derivative with respect to A, this will result in this value. Now again, the gain is much higher for op-amp with respect to R2 by R1. So we can say that for this denominator, A is much greater than 1 plus G0. Or we can say that it will be equal to 1 by A into 1 plus G0 by ignoring this value as it is much lesser than A. So if we say again A is much higher number, so A is a large number, so the sensitivity of T with respect to A will be small value. So this signifies that the amplifier gain is approximately equal to G0 by G0, which is equal to minus of R2 by R1, and it is independent of A, as the gain is very large. Now if we remove R2, or we can say that if R2 is open circuit, or if we have R2 is equal to infinite, the third way of doing this one is saying that there is no feedback. If there is no feedback, the sensitivity will become with respect to A as R1 plus R2 upon A plus 1 into R1 plus R2 at R2 at infinite. R2 is open loop. Now if R2 is infinite, this will be again cancelled out and it will give equal to 1. And we have seen that for the open loop, the sensitivity with respect to component is always 1. Or we can say that the change in 1% in the one component's value, here component value is A. So 1% change in the A will result in 1% change in the T. So we can say that the change in A translate directly into G naught. Whatever the change in the A is there, that is directly changing in the T. So the order of unity are acceptable for the passive components. They are far too large components, for example, for the open op-amps gains. So this is all about the sensitivity. We have seen the open loop and the closed loop gains. We have seen one example where we have seen that the gain is varying for the different component values, R0, R1 and A. All these values can be, similarly we can calculate the dependency of transfer function with the other components. For example, if C is there, we can find out the sensitivities of the all components. Thank you.